So, welcome students for the physical chemistry lecture, and this is the last point of your chapter chemical kinetics, the temperature dependence of the rate of reaction. All of you know most of the chemical reactions are accelerated by increase in temperature. That means when we increase the temperature of the reaction, the rate of that reaction increases. For example, in decomposition of N2O5, the time taken for half of the original amount of material to decompose is 12 minutes at 50 degrees centigrade, 5 hours at 25 degrees centigrade, and 10 days at 0 degree centigrade. That means as we increase the temperature, the decomposition rate of nitrogen pentoxide increases. Okay. You also know that the mixture of potassium permanganate and oxalic acid gets decolorized faster at higher temperature than that at lower temperature. And it has been found that for a chemical reaction with a rise in temperature by 10 degrees centigrade, the rate constant is nearly doubled. That means the value of rate constant, it gets doubled when we increase the temperature of the reaction by 10 degree centigrade. The temperature dependence of the rate of chemical reaction can be accurately explained with the Arrhenius equation, and it was first proposed by Dutch chemist J.H. van 't Hoff, but Swedish chemist Arrhenius proved its physical justification and interpretation. The rate of reaction depends on temperature. It is first explained by the scientist van 't Hoff, and it is physically proved by the scientist Arrhenius. Okay, then the Arrhenius equation, it is given as K, it is equal to A into E raised to minus EA by RT, where A is the Arrhenius factor or frequency factor, and it is also called as pre-exponential factor. It is a constant specific to a particular reaction, and R, it is a gas constant. EA, this EA, it is the activation energy measured in joules per mole, that is J into mole inverse. It can be understood clearly using the following equation. What is this activation energy? Consider the simple reaction between hydrogen gas and iodine gas, and the product of combination of hydrogen and iodine, we get hydrogen iodide HI here. This at first the H2 molecule, and here it is a I2 molecule. Then there is a formation of intermediate compound. It is shown like this. Here H, it gets combined with iodine molecule, and here this second H, it gets combined with the next iodine molecule, that is the intermediate or activated complex is formed, and immediately there is a formation of HI, two molecules of HI, this. Then according to Arrhenius, this reaction can take place only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate. It exists for a very short time and then breaks up to form two molecules of hydrogen iodide. Here, the energy required to form this intermediate called activated complex This, this is known as activation energy. Here in this diagram, it is shown uh, by plotting potential energy versus reaction coordinate. Reaction coordinate represents the profile of energy change when reactants change into product. Here, some energy is released when the complex decomposes to form products, so that the final enthalpy of the reaction depends upon the nature of reactants and products. All the molecules in the reacting species do not have the same kinetic energy, since it is difficult to predict the behavior of any one molecule with precision. Then the Ludwig Boltzmann and James Clerk Maxwell used statistics to predict the behavior of large number of molecules, and according to them, the distribution of kinetic energy may be described by plotting the fraction of molecules, that means Ne by Nt, with the given kinetic energy versus kinetic energy, and here Ne and Nt is the total number of molecules. So see here, at first, if we plot the graph of potential energy versus reaction coordinate, that means our reaction is in between H2 molecule and iodide molecule. These are our reactants here, and the energy of reactants, it is like this. And when H2 and I2 they combines, their energy increases. Okay, their energy increases due to the collisions between hydrogen and iodide molecules. And here we have the activated complex, and remember that here activated complex, it is a unstable molecule, and it has a very short lifetime, and immediately the energy of the activated complex decreases, and we get the 2Hi molecules. Okay, and each and every reactant has to pass this energy barrier, and this energy barrier, it is called as activation energy, and this activation energy, it is gained by the reactants due to the collisions between the hydrogen molecule and iodine molecule. Remember, hydrogen and iodine molecules, they collide with each other. Their energy increases. Then activated complex is formed, or intermediate product is formed, and then energy, their energy decreases, and we get the final product. That means the 2Hi molecules. This diagram showing plot of potential energy versus reaction coordinate. Okay, then here when we plot the graph of fraction of molecules versus kinetic energy, here this is the nature of the graph, and this is called as most probable kinetic energy. Here the peak of the curve corresponding to the most probable kinetic energy, that is kinetic energy of a maximum fraction of molecules. There are decreasing number of molecules with energies higher or lower than this value. When the temperature is raised, that means increased, the maximum of the curve moves to the higher energy value, and the curve broadens out, that is spreads to right, such that there is greater proportion of molecules with much higher energies. The area under the curve must be constant, since total probability must be 1 at all times. we can mark the position of EA on Maxwell-Boltzmann distribution law. Okay, and the integrated form of the Arrhenius equation we can write like this. Here, the Arrhenius equation, the factor e raised to minus EA by RT corresponds to the fraction of molecules that have kinetic energy greater than EA, and taking natural logarithm of both sides of the equation, here above equation we get ln k, it is equal to minus EA by RT plus ln A. Then the plot of ln k versus 1 by t gives a straight line according to the equation. That is, this is the graph of ln k versus 1 by t, and the slope of this line, it is the minus EA by RT. Okay, here. Thus, it has been found from the Arrhenius equation that increasing temperature or decreasing activation energy will result in an increase in the rate of reaction and exponential increase in the rate constant. Here, the slope of this line, it is minus EA by R, and intercept is ln A, where A, it is the Arrhenius factor. The intercept value, it is a ln A. So we can calculate EA and A using these values at temperature T1, and ln K1, it is equal to minus EA by RT1 plus ln A. At higher temperature T2, we can write this equation as ln K2, it is equal to minus EA upon RT T2 plus ln A. Since A is constant for a given reaction and K1 and K2 are the values of rate constants at temperature T1 and T2, here the substituting this equation, we get ln K2 minus K1, it is equal to EA by RT1 minus EA by RT2, and here subtraction of 2 log, that means ln K2 by K1, it is equal to, this factor is common, EA by R, and in bracket we can have 1 by T1 minus 1 by T2, and changing natural log to the log base 10, we can write this equation as log K2 by K1, it is equal to EA upon 2.303 R into 1 by T1 minus 1 by T2, or here we can write this equation as log to the base 10 K2 by K1, it is equal to EA upon 2.303 into T2 minus T1 upon T1 into T2. This 1 by T1 minus 1 by T2, simplification of this bracket, we can have this T2 minus T1 by T1 into T2, and by using this equation we can find the energy of activation knowing K2 and K1 at temperature T1 and T2, or amongst these 5 quantities K1, K2, T1, T2 and EA. If we know any 4 values, we can determine the 5th value, and this is the last point of your chapter. And the theories of reaction rate, this point it is deleted from the your syllabus. So prepare well, and here we will see one example depending on the Arrhenius equation, that is the calculation of energy of activation. The rate constant, here example, the rate constant of a reaction at 500 Kelvin and 700 Kelvin are 0.02 second inverse and 0.07 second inverse respectively. They have given two temperatures and two rate constants and calculate the values of EA and A. Here we have to calculate energy of activation and A value. By using this equation, we can calculate here EA log K2 value is 0.07, K1 value 0.02. EA we have to calculate this R value, it is 8.314 joule per Kelvin per mole. Okay, so substituting the values of T1, T2 and K1, K2, here we have solved this and get 0.544 into EA, and here 5.714 into 10 raised to minus 4 divided by 19.15, the product of these two. Okay, so from this equation, EA, it is equal to the product of this and this. Here it is 0.544 into 19.15 divided by 5.714 into 10 raised to minus 4, and it is equal to 18,230.8 joule, and K, K it is equal to A into E raised to minus EA by RT. We have the value of K at temperature, lower temperature, that is the 0.02. It is equal to A into E raised to minus 18,230.8 divided by 8.314 into lower temperature 500, and solving this we get A, it is equal to here 0.02 divided by 0.012, and it is equal to 1.61. Okay, such kind of examples are asked. So here we have completed this unit, that is the chemical kinetics. Prepare well for MCQ test. Last time I have explained you the nature of your examination. Also I have given you the timetable. On 12th of August you have to attempt this chemistry paper number 3, and its code is 72,844. Okay, so prepare well, and here we have completed this topic. If you have any doubts in the understanding, you can freely ask me. Thank you very much.